Hello everyone. In this video, I'm going to begin talking about the covalent bonding theories that describe how covalent bonds are formed and how we can represent them, what shapes they take, and what orientations they take in bonded species. So the rest of this video series is just going to be talking about covalent bonds only. We're not going to be talking about ionic bonds. So just a little bit of an introduction. Atoms associate themselves into molecules because of the attractive forces between their nuclei, which have positively charged protons in them, and the electrons of neighboring atoms, which are negatively charged. So if I have one nucleus here that has a positive charge in it, and then I have an electron around it, this might be a hydrogen nucleus. So it's got one proton down in the nucleus and then one electron around it. Well, if I had another hydrogen and its nucleus had a proton in it and it had a single electron around it, a covalent bond is formed because the positive charge in one atom's nucleus is attracted to the negative charge on the electrons in a neighboring atom. So this right here is a covalent bond. It's an electrostatic attraction between the positive charge of the nucleus of one atom and the negatively charged electrons of a neighboring atom. And it's what holds two atoms together in a molecule. Now, there are ideal distances at which that attraction is energy minimized, which is to say it's most stable, and that depends on two factors. There is a strength of attraction between the positive and negative here, but there is also a repulsive force between the electrons of the two atoms. So this attraction draws them together. This repulsion pushes them apart, and at some point those two forces are equal and we reach some stable distance between the two atoms. So that's what this is saying. At some point the repulsive forces of the two atoms' electron clouds, which are both negatively charged, will prevent the atoms from getting too close to each other. When they find the optimum distance, they will be at an energy minimum, a lower energy, that is their most stable distance apart. So the attractive force that holds these atoms together is the result of the nuclei, that's the plural of nucleus, the two nuclei of both atoms being attracted to the same valence electrons. This nucleus is attracted to its own electrons and it's attracted to its neighbor's electrons. This nucleus is attracted to its own electrons and to its neighbor electrons. So these nuclei are attracted to the same electrons, and that's what holds them in close proximity. We call this shared attraction for the same pair of electrons a covalent bond. Co means together or sharing, and valent is referring to the valence electrons. So they're sharing an attraction with the same valence electrons, and that's what holds the atoms together. And as I said, the result of this covalent bond is that there is a stable distance that is reached between these two atoms, and we call that the internuclear distance. Inter meaning between the two nuclei, internuclear distance between the two atoms. We call the internuclear distance, that distance is the length of the bond, so we call it the bond length between the atoms. So whatever stable internuclear distance we have between these atoms, that will lead to a distance between this nucleus, and that distance is called the length of the bond, or the bond length. So I have a nice little graph down here. And this graph, on the y-axis, it has energy in joules, and on the x-axis, it has a bond length, or the internuclear distance, in picometers. And picometers are smaller than nanometers. So we're talking about very, very short distances. If we look first at just two hydrogen atoms that are far enough apart that they don't attract or repel each other, we can see that the energy of that situation is almost zero. See how it approaches zero? As these hydrogen atoms get farther and farther apart, there gets less and less and less energy of the attraction between them. But as we shift to the left along this axis, along this x-axis, we're getting a shorter and shorter and shorter distance between the two nuclei. So you can see as we draw them closer together, they begin to interact, and now the nucleus of this atom is starting to be attracted to its neighbor's electrons. And the nucleus of the neighbor is attracted to this cloud of electrons. And so there gets to be an attractive force between them so that the energy is minimized, so they start to become more and more and more stable as they get closer together because of the attractive force. Once they reach some optimum distance between them, and for the hydrogen-hydrogen bond in an H2 molecule, it happens to be 74 picometers, then you get its most stable energy level. And that energy level is a negative 7.24 times 10 to the negative 19 joules. This is the most stable distance between two hydrogen nuclei in an H2 molecule. So what happens if I force them to get closer and closer and closer together? If I move further along the x-axis to the left? Well, at this point, the electron clouds start repelling each other. And so that repulsive force starts to take over, and you can see that the energy starts to get larger and larger and larger because it's less and less and less stable. And if I were to try to smash them really close together, the energy increase starts to increase quite a bit as the distance between the nuclei gets smaller and smaller and smaller. So there's a most stable distance between the two nuclei. And that distance between one nucleus and another, the internuclear distance, when it is at its most stable, is called the length of the bond between those two atoms, or the bond length.